Anybody have any homework questions you want me to go over for thermo? I guess we haven't had homework for a while. Okay, so now we're getting into the last thing we did the last couple of classes was that big outline of where we are going into the second law of thermodynamics. So now we're into the second law of thermodynamics. We're going to use this for closed systems, and we're also going to use it for control volumes. And there are two main things that you use the second law for. So two main uses. The first one is calculating the efficiency of processes. And the second one, if you think about conservation of energy, I don't know if it's ever occurred to you exactly this way before, but you can't tell using conservation of energy ever what happened first and what happened second, you know? Like you can say this much potential energy was exchanged for this much kinetic energy for a skier going down the hill. But there's no difference from saying a skier going that fast at the bottom makes it up this high, you know? And so the second thing that we're going to be able to do, that you'll be able to do for the first time in any class, I think, is determine the direction of time, you know? So I'll say calculate the direction of processes. There are three statements to the second law of thermo. One is so intuitive it seems obvious, and then the other two don't seem obvious at all, and it's kind of surprising that they're the same thing. This first pass through a lot of this stuff, I'm not going to go through like derivations or anything like that. I'm just sort of giving you the basics to do some sort of quick and dirty calculations. Later on, we'll come back and talk a little more about where these come from, and you'll understand it a little better. But there are three equivalent statements of the second law. The first one is called the Clausius statement. And it says that heat only moves spontaneously from a high temperature to a low temperature. This is the most intuitive of these three. You never in the winter open the door and have the temperature go up in your house, you know what I mean? That's what this is saying, is like energy only transfers from the higher temperature to the lower temperature. The second one is called the Kelvin-Planck statement. And that says, so the way we're going to write it to use it mathematically is for a system in contact with only one thermal reservoir, For a system in contact with only one thermal reservoir, the work done by any cycle is less than 0. Okay, so this is a form that's going to be useful to us mathematically. Intuitively, think of it this way. So think of it as you can't have a power cycle without losing heat to exhaust. In other words, okay, so you can't, so think of what a power cycle is.
Yeah, the system more than 100% efficient, essentially.
Yeah, it has to be less than 100% efficient. So whatever amount of energy you get from the boiler, from the fire or whatever, you can't turn that all into work. Some has to be output. Okay. And we are going to use this, so this mathematical form, we're going to use this to derive two important things. We'll use this to derive what's called the Clausius inequality, kind of a precursor to the entropy statement and the definition of entropy. And the entropy statement. This Clausius inequality is going to be important to us. We're going to spend a little time on it in a couple weeks, I think. So notice that there are two Clausius things and they're different. The Clausius inequality is a mathematical thing that we're going to use. That's different than the Clausius statement of the second law. Okay. The Clausius statement of the second law, mainly we're just using to ground ourselves. Like everything can be derivable from this, but mathematically, these other things are going to be more important to us.
The Clausius statement, that's saying heat moves to cold.
Right.
Isn't it technically like both happening at the same time? They're just going to equilibrium.
Well, heat is...
like heat and cold are exchanging with each other simultaneously, trying to reach the equilibrium.
Heat is an exchange of energy, remember. We talk about heat like it's high temperature in everyday language, but so remember really what it is there's a high and a low temperature region, and heat is the movement of energy from one to the other one. Well, I don't know. I guess maybe you could think of it the way you're talking about it. But I was going to say, remember that when the way we're thinking of energy transfer and stuff, really what's happening is a bunch of little balls are bouncing around, But we're talking about these systems in a macroscopic way where you end up, weird things can happen with one little ball, but when you're looking at a big enough collection of balls, you get what looks like a smooth motion of energy from the higher temperature to the lower temperature.
Over time.
Yeah, and we're not going to talk about it in terms of statistical mechanics and bouncing balls and stuff. Yeah. Any other questions right now about that?
Well, because the cooler temperature isn't doing anything on the higher temperature, but the higher temperature is giving energy to the
right. That's right. That's right. And then the last one, I guess the most important one to us, is the entropy statement. You can think of this as, for a closed system, a system that doesn't exchange any energy. The change in entropy is greater than or equal to 0. Another way to think of it is, if you don't have a closed system, the change in entropy of the system plus the change in entropy of the surroundings is greater than or equal to 0. So you know that entropy only goes up. You've heard that before, I'm sure. Just remember that you can make entropy go down in a system. Refrigerators are making entropy go down. But in order to make the entropy go down inside the refrigerator, you're making entropy go up in the surroundings. The coils on the back of the refrigerator are making entropy go up. And the sum of those two amounts is always up. Okay? So don't make the mistake of assuming that entropy only goes down. You can totally make, or that entropy only goes up. You can totally make entropy go down. It's just when you take all
The net.
everything into account in the universe, entropy goes up. Okay. And you can assume that your system entropy goes up if you are dealing with a closed system where no energy transfers. Okay. All right, so the first thing we're going to do is use the Kelvin-Planck statement to talk about efficiencies of processes. We'll talk more in detail about this later, but these are the first calculations you're going to do. So we're going to talk about efficiency. And the Kelvin-Planck statement says basically you can't use all your heat input to produce work. So let's think about the three important cycles that we're going to deal with. The first one is the power cycle. That's where heat is input to your system, the gas, and that heat added to the gas produces work. So we'll say there's a reservoir here that's hot. And then this is the system. And then there's a cold reservoir here. I want you to notice as we do this, we're getting away from the first law sign convention as we do this. Okay. So I think actually in the power cycle, it's our usual first law one, but when we get to the other two cycles, we're going to change it. Observe the sign conventions. It's not going to be the same thing that you've been using in the first law.
Why did they do that? Why did they choose to keep switching the signs?
That's a good question. I guess my guess is it's just different people doing different things, and they don't Oh, it's not always communicated. Yeah, exactly.
Yeah.
Okay, so for a power cycle, you have heat coming in from the hot reservoir to the system. So I'll call that the heat. That's Q sub H is for the hot reservoir, or I think sometimes I make it can be a little confusing. Sometimes I call it QH and QL for high and low, and sometimes I call it QH and QC for hot and cold. I'll try to be consistent, but so the heat comes in from the hot reservoir, work is done by the system, and the Kelvin-Planck statement says there has to be some heat ejected to the cold reservoir. That's the exhaust. Okay, so what do you know? Well, you know that the first law of thermodynamics, okay, this is a cycle, right? So in a cycle, there's no change in any property inside your system. Okay, that's what a cycle means. You get back to the same state you started at. Okay, and so that means that the changes in energy have to equal zero over a cycle. So that's why in this use of the first law, there's no change in energy. But we get that QH, I'm just balancing the things, the energy going in and the energy going out. So QH is equal to W plus QC. And so you can express the work in terms of the other two. Work is equal to the heat coming in from the hot reservoir minus the heat going out to the cold reservoir. Then to analyze the performance of a power cycle. So all of these performance measures are going to be a ratio of the thing you're trying to produce divided by the thing that you're adding to get that. So what we want in a power cycle is we want as much work as possible. And the thing that is costing us energy, money, whatever, is adding the heat to the system. So our efficiency and that is the Greek letter eta, is equal to the work over the heat added at the boiler. And if I substitute this in for work, we can write this just in terms of heats as QH minus QC over QH. And we can simplify that to 1 minus QC over QH. And you'll see the benefit of writing it all in terms of heats in pretty soon, maybe today. Okay, so that's a measure of the efficiency of a power cycle. We're going to see that there's no way to get one here, but we'll talk about that soon. The next one is a refrigeration cycle. So again, we have a hot reservoir. We have our system. And a cold reservoir. This time the direction of everything is reversed. So what you're trying to do in a refrigeration cycle is you're trying to get heat to go from the cold reservoir to the system. So QC is positive this way. You're trying to eject that energy at the hot reservoir. So QH is positive when it's leaving. The Clausius statement of the second law says that isn't going to happen spontaneously. So the way you get that to happen is by doing work on the system. Okay? So your system is the refrigerant as it goes around the whole its whole path. The work is done by compressing the refrigerant to raise its temperature. Okay, when it's compressed, that refrigerant runs through the coils in the back, and because the compression has made the temperature higher, it can eject heat to the surroundings, to the room. Okay. Now that it's ejected energy to the room, the higher temperature, the hot reservoir, now it's allowed to expand again. The temperature cools down. Now it goes past the cold reservoir, and since it's cooled down, it can pick up energy from the cold reservoir where this is where your popsicles are. This is the room. So it gets that energy, then it's compressed again, and through that cycle, it just keeps ejecting energy to the hot reservoir, to the room, and then taking energy out of the cold.
So when it goes past the cold reservoir, it's at a state of lower energy.
It's at a state, yes, that's right. So each time around this path, it's drawing energy out of the cold area, away from the popsicles. Then it's getting compressed to raise its temperature, which allows it to eject that energy that it's gained. And then it's at a low enough temperature. Since it ejects that energy to the room, it can be back at a low temperature again when it goes back to the popsicles. Yeah. Okay, so you have the same relationships here, even though, since the sign convention of everything is reversed, you have these same equations. So you can think of it as, QC plus W is equal to QH. And so again, you can express the work in terms of these other two. The reason to do that isn't apparent yet, but it will be soon. And using that, you can express the coefficient of performance. That we're going to call the Greek letter gamma. And that is equal to, okay, so oh, nope, it's not gamma. Sorry, it's beta for a refrigeration cycle. Gamma is going to be the heat pump cycle. So what's the thing that you're trying to maximize in a refrigeration cycle?
The dissipation of heat.
Yeah, really what you're trying to maximize, you don't care where that heat goes, although it's necessary. You're just trying to get as much heat away from the popsicles as you can, And so this is going to be QC divided by W. The work of compressing the gas is the cost of running this refrigeration cycle. And then again, it's not totally clear why we would ever want to express this all in terms of heats, but we will want to. And so you can substitute in this expression for work and rewrite this as QC over the quantity QH minus QC. Any questions right now about that? And then the last one of the three big cycles is the heat pump cycle. I want you to notice this is the exact same cycle as the refrigeration cycle. The only difference is in a refrigeration cycle, you don't really care about what's happening at the room. You know, what you're trying to do is at the popsicles. At the heat pump cycle, what you care about is the room. And you don't care about, instead of popsicles, this is just outside your house or whatever, you know. So what you care about is the thing that changes, but the cycle is the same. So I'll draw this again. So here's the hot reservoir. Again, this is the room. Here's the system. Here's the cold reservoir. This time this is just outside. But everything works exactly the same. You have, you're pulling heat from the colder area outside, and we'll call that QC. You're ejecting that heat to a hotter area, we'll call that QH. That's impossible on its own. That's what the Clausius statement says. And so what the cost of running this thing is a compressor that does work on the gas to raise its temperature so it can eject to the surroundings. And again, you have, you can write this as work plus QC is equal to QH. And so work is equal to QH minus QC. The coefficient of performance for the heat pump cycle, this is the one that we're going to call gamma. And this time, we don't care about the Q sub C. All we care about is how much heat we're adding to the room. So this is what we want is QH divided by the cost of running this thing, which is work. And then again, you can rewrite this as QH over the quantity QH minus QC. All right, well, you're going to do calculations where you're given, you're given certain values for the work or QH or QC or whatever, and you're going to have to use equations to figure out what the other ones are. So all of these forms are going to be important, okay? So if you want to put a sheet of equations in front of you as you do these problems, all these equations could be necessary. So now, what are we going to do with these coefficients of performance? Mostly, we would like to be able to put realistic limits on these. So we want to use these to put realistic limits on our thermodynamic cycles. In order to do this, the first thing we have to talk about is reversibility and irreversibility. So reversibility and what we're going to call irreversibilities. Well, you can think of reversibility, think of irreversibilities as basically the thermodynamic equivalent of friction. Okay, it's energy loss that you can't get back. In Physics 1, you talk about pendulums or people skiing down hills or whatever. If you assume there's no friction in any of that, then if you have two identical hills and a skier starts at rest at the top of one of those hills, he'll go down, get to a maximum speed at the bottom, and go all the way up to the top of the next one. Realistically, though, some of that energy is going to be lost, and the skier wouldn't quite make it to the top of the second one. And that's what we're talking about here.
Can't suck heat back up.
Yeah, right. So a reversible process is one where the system and the surroundings could both be returned. This both is important. Could both be returned to their starting state. Okay, so imagine the skier again, and imagine you have the skier starts at the top of this hill, okay? And imagine down at the bottom there's a little track that the skier will just go around this path and get sent straight back up the hill again, okay? So if there's no friction and no air resistance or anything as this skier goes down the hill, the skier will start at rest, speed up as he goes down, go around this track, no energy is being expended, go around the track, go back up the hill, and end exactly where he started, okay? So that's a case where this process was reversible. The surroundings didn't have to expend any energy, so they're in the same state that they were at the start. The skier didn't have to expend any energy, and the skier is returned to where he was, okay? Now, with irreversibilities, friction in this case, and air resistance, the skier will go down, losing energy the whole way due to friction, go around the curve, get back to the hill, go ways up the hill, but not all the way. And now in order to return the skier to his original state, he has to take a chairlift or something. Well, that chairlift keeps the surroundings from returning to their original state because you have to use energy, whatever, like I don't know what they power chairlifts with, but somehow that's affecting the surroundings, you know what I mean? So that's what we're talking about here with the difference between reversibility and irreversibility. And the things that make something fail to be reversible are what we're calling irreversibilities. So friction is an irreversibility. And now I'm just going to list out all the things, the irreversibilities that are going to be important to us, okay? So irreversibilities are all the things that prevent a process from being reversible. Okay, so here are all the irreversibilities that you have to consider in this class. The first one is friction and air resistance. The second one is electric current through a resistance. Electric. The third one is inelastic deformation. So inelastic means that you can load something and it'll deform, but the inelastic, but the thing that determines whether it's elastic or not is when you remove the loads from it, is it going to spring back to its original shape, you know? So I think for a long time, I always thought of elastic as being stretchy, but it's not the stretchiness that makes something elastic, it's the popping back, you know? So like a ball of clay is not elastic, even though it's very easy to deform, because when you let go of it, it stays that way. So that's a plastic deformation. Elastic springs right back to shape. This is an important one. Heat transfer across a finite temperature difference. So when we're talking about reversible systems, we're always going to be assuming that heat is transferred over an infinitesimal temperature gradient, okay? Which isn't practical because it would take forever to raise the temperature or whatever, but that's one to keep an eye on. Anytime you let two areas with a finite temperature difference into thermal contact with each other, you're losing energy that can't be restored. Okay. Fifth is unrestrained expansion of a gas. Sixth is chemical reactions. And seventh, the last one, is mixing materials at different states. So pouring liquid water into ice. States isn't the right word. What would you, I'm blanking on,
Liquid gas.
yeah, like that kind of stuff at different phases. That's right. Thank you. Different phases. Yes. And here are two important definitions. You should try to keep these in mind. So the first one, I already said what reversible is, but that's one of them. So reversible means you can run a process in reverse and return both the system and the surroundings to the starting states. So you can run it in reverse and return the system and the surroundings to the starting states. Well, another thing that's going to be important to us is just that our system, so what does it take for something to be reversible? It takes there being no irreversibilities in the surroundings or the system. If your system doesn't have any of those irreversibilities in it, electricity going through resistors and all those 7 things, then we call it internally reversible. Okay, there's no guarantee that you can return it to its starting state without changing the surroundings, because we don't know about the surroundings. But this is like a perfectly inefficient collection of things in your system. Okay, so internally reversible. That just means none of those 7 types of irreversibilities inside your system. Okay, so think about, so the next thing I'm going to say is, if you have say a power cycle, okay, you might think like, okay, there would be more efficient power cycle. Like even if you have totally reversible, frictionless power cycle, like a perfect power cycle, maybe there would be frictionless ones that work better than other frictionless ones. And it turns out that that's not the case. All of these sort of perfect, ideal, frictionless power cycles have the same performance. Okay? And if you want an analog to that, think about the idea of a skier going down a hill, and we're going to see what the skier's speed is at the bottom. Okay? In the real world, where there's friction and stuff, there's a huge difference between how fast the skier is going to be going at the bottom based on the shape of the hill. If the hill is really gradual, the skier is going to be going really slowly at the bottom. Okay. If the hill drops really fast, the skier is going to be going really fast at the bottom. But with no friction, this hill could be stretched out over 50 miles, 1,000 miles. That friction isn't going to have, there's no friction that's going to have an effect. And so whether the hill drops straight down or the hill takes 1,000 miles to drop down, the speed is the same at the bottom. And it works the same with power cycles if you don't have friction. Okay? So for now, trust me, all reversible power cycles have the same performance. That's true also for refrigeration and heat pumps.
mean, there's really no true, like, reversible.
Right. That's right. But you can get closer and closer to it.
We'll never get there.
Right. Correct. Okay, so based on this idea, we're almost to the point where we can do some calculations. So based on, come on. Based on this definition, or not definition, but based on this fact, the Kelvin temperature scale says, or comes from, saying that for a reversible power cycle, and it doesn't matter what reversible power cycle, the ratio of the heat ejected in the exhaust over the heat added at the boiler is equal to the ratio of the absolute temperature of the cold reservoir to the absolute temperature of the hot reservoir. Okay? And so what that gives us is, ideal performance comes just from the temperatures of the reservoirs. Okay, so when I defined these performance coefficients, and I did it all in terms of the heats, the reason that we did that is because of this relationship. Okay, so now that we have those coefficients of performance expressed in terms of heats, we can re-express them in the ideal case in terms of those temperatures. For the power cycle, we express the coefficient of performance, the efficiency, as 1 minus QC over QH. And that means that the ideal efficiency for a power cycle is 1 minus the temperature at the cold reservoir divided by the temperature at the hot reservoir. And for the refrigeration cycle, the coefficient of performance was QC over the quantity QH minus QC. And so the ideal coefficient of performance for a refrigeration cycle is the temperature at the cold reservoir divided by TH minus TC. And same thing with the heat pump cycle. We define the performance as QH over the quantity QH minus QC. And so the ideal is TH, temperature at the boiler, divided by TH minus TC. Okay, so I'm going to give you a small number of problems where you're just going to be given some stuff about temperatures and heat transfer and stuff like that, and you're going to judge like whether it's possible or what the maximum heat is that would be possible according to the ideal performance. And you're just going to use these equations and those other equations that I gave you today, put them together and figure out whether the actual performance is higher than the ideal performance, basically. Okay, you with me on that? All right, that's all. Have a good weekend. It's the weekend.